Now let's go to the most interesting part. So now I have found my input impedance, and I will start with the input impedance for the implementation I showed you before, the Butterworth implementation, and that one basically was the h of s was the s cube that basically yielded that input impedance. Now here we have to basically start progressing step by step, because what we realize is that we have to implement this transfer function, and the numerator is 1 degree higher than the denominator, so I can actually divide the two polynomials, and I will basically have s plus this polynomial here, or s plus another impedance z2. So if I look from a circuit perspective, essentially what I'm implementing is a reactive network between my load and my source, and I'm working in the normalized domain at this point. What I mean by normalized domain is that my source impedance is assumed to be equal to 1 ohm. I'm making this assumption. Later on, I will basically scale this impedance to whatever value I want. And I'm also working with a frequency of 1. So my omega is equal to 1 here, again, in a normalized domain. Later on, we'll figure out how we can actually go from this synthesis that assumes 1 rad per second to any other frequency that I want. And so the reason that it's important to actually see this is because when you're looking at an input impedance that is equal to s plus z2, essentially what you might be thinking in your mind is what is the impedance of an inductor L or a capacitor C. An inductor L actually has an impedance of s times L, j omega L, or s times L, while a capacitor has an impedance of 1 over SC. And so once you have this in your mind, it doesn't actually take much to realize that this equation here that says that my input impedance is S plus another impedance simply almost screams for a series inductor. Because if I choose a series inductor with an inductance value of 1, then I basically implement the input impedance, at least the first part. And then I'll worry about finding out the input impedance of the second part. So when you start seeing equations like this, it's important to start thinking of what kind of reactive element implements that. And this is basically the hint that I wanted to give you on this part. So essentially, once I have this hint, then I basically say, look, I'm trying to implement my input impedance to be the way I want it up there. So let me just take out the series inductor with an inductance of 1, so shown right here. And then anything I add after this will basically implement Z2, which is this impedance right here. Now, if you look at this Z2 now, I have to find the network that realizes this. I can't really play the same trick because now my numerator is actually 1 order less than the denominator, but I can actually now work with my admittance, y of 2. So I will basically work with my admittance. Y of 2 will be obviously the inverse, and I will do again the same type of a voltage division, sorry, not voltage division, polynomial division, and I will end up with this guy here. So I will have 2s as the first element and another admittance y of 3 following that. So now let's say I have this 2s based on the thing I mentioned before. If I have a capacitance, its admittance is nothing else but s times c, which means that I can implement this guy if only I choose a c of 2. And so basically that's the trick. I will go ahead and follow my series inductance with a shunt capacitor that implements an admittance of 2s, and then ask for the next network that basically will give me a y3 admittance. y3 is 1 divided by s plus 1. So again, I will, instead of working with this guy, I will work with z3, which is s plus 1 divided by 1. And again, it doesn't take much to see that this basically is s times another inductance L, whose value obviously will be 1, plus a real part, which will equal 1. So indeed, here's basically the final network realization. I implemented this last part of Z3 with basically my series inductance that basically implements this one, and my load, which will actually implement this one right here. So I have now successfully started from a required impedance of Z input as a function of S, and I have synthesized a network that, at least in the normalized domain, where again all impedances are actually equal to 1 for source and load, and my omega is equal to 1, basically satisfies all the requirements that I want. So in principle, you can basically do this for whatever Z input you basically have. Now, the interesting thing about this process is that if you basically follow this, you will end up with a ladder network, very similar to what you will see right here, where you just have successive polynomial divisions, and you will always end up with the element values being right here. So you're probably much better than I am in polynomial divisions. And at the end of the day, once you're done, you will end up with the very last polynomial division that will always include Gn times S plus either a resistance or a conductance. And the value that you will have there, this R, or 1 by R, will actually determine what is the required value of the load to implement the transfer function. So let's continue with step 4 here by looking at the second possibility. So the second possibility is that we choose h of s to be negative s cubed. One can go basically through identical process like we did before, or you can simply observe that the z input, when you choose the h of s to be negative s cubed, is simply 1 over the z input of the previous scenario. So it turns out, either where you go through the same synthesis process or you just make this observation, that you basically will end up with exactly the same elements, except now the first inductance is not series inductance. It has actually become a shunt capacitor. The second element, which was a shunt capacitor, has now become a series inductance, and so on. But the values are identical. So before we had a series inductance here of 1, here we had the shunt capacitance of 2, and here we had the series inductance of 1. So identical values, but the roles have been reversed. So you will always have to basically choose between the two realizations. The realization that we did in some detail and the realization that comes from the second part is what we did in more detail, and then the other realization. But because the elements are identical, we basically usually end up computing simply those element of values of G's. And it really depends whether you'll have them implemented as capacitance or inductance. Now, why is it important? I mentioned that in many practical cases, one is preferable than the other. So the answer to that is that it really depends on how you want the filter to reject in the stop band. That means when you, this is a low pass, obviously, filter. So that means that if I plot the S21 square as a function of frequency, it will basically yield something like this, right? This is a Butterworth filter. But the question is, in my stop band, meaning from here on, the filter is rejecting, but is it rejecting as a short circuit or as an open circuit? In other words, what is the phase of the reflection coefficient that you will see right here? So when the signal doesn't go through, this is a reactive network. It's not being consumed in the filter. We will see cases where this signal is actually being consumed. But right now, all the signal is reflected. Well, so if you look at the first geometry, you will see that this capacitance is basically the first element that you will see. So how does a capacitance look like when the frequency is very high? Basically, it looks like a short. So when the frequency is very high in the stop band, essentially it looks like you have basically a short right here. Equivalently, if you look at the second component, when the frequency gets really high, this inductance basically looks like an open. So essentially it looks like you have a broken circuit when the frequency is very high. And it's really crucial to realize this because it will directly affect what's going on. For example, imagine the scenario here. So imagine the scenario where you have an antenna, and now you have basically a diplexer to separate the transmitter from the receiver. So here's basically going to be my PA and so on. for my transmitter path, and here is basically my LNA for my receiver part. Clearly, I want to separate those two. So imagine that this filter here was basically rejecting, let's say, as a short, and you were trying to transmit. So I'm basically trying to send my signal through the antenna. Probably the word total catastrophe doesn't begin to describe what's happening here, because you're not going to successfully transmit. The signal, the minute it basically reaches this diplexer, it will basically see a short right here. So tough luck, instead of going through the antenna, it will actually be reflected. What you really want is not a short, but an open. So rather, when the signal comes through, it sees two paths. One has been left open, so it won't go to the receiver path. The other is basically leading to the antenna, and you basically have success. So if you're designing a single filter, maybe you care, maybe you don't care of how the filter rejects. But when you design systems and you design diplexers, it actually matters a lot. And so often in real life, we have less flexibility than what the math make it look like. Now, this is a little bit of a general solution for Butterworth, and I'll give you the equations for Chebyshev as well. But you don't really have to repeat what's already known. But if you want the explicit solutions, and you can program this in MATLAB or Excel or anything else you like, you can very quickly get essentially the G element values for Butterworth, and you can very quickly get the same things for Chebyshev. I think I'll show you the Chebyshev in a minute.